Okay, good. So we were talking about other kind of acceptance conditions, right? We started with. Uh, okay, but maybe before that, let's try to recap a bit what we did. So we were looking at um, determinization of non-deterministic book keyword operators, right? And one thing, of course, we also discussed that non-deterministic book keyword automata are strictly more expressive than deterministic book keyword automata. And we had a formal proof this time. So we showed that this language of finitely many A's, this cannot be accepted by a deterministic automaton, book keyword automaton, right? So, um, and then we also showed that if you have a subset construction, then it may accept some words which are not exactly in the language of the original automaton. Okay. So this is what I said, like DBW is a strict subset of omega regular languages, and omega regular languages are what for which can be accepted by NBW. And we also defined limit of a language, and we also said that there is a characterization for languages which are DBW recognizable in terms of this limit of a language, right? So it's DBW recognizable if and only if there exists a regular language R such that A is limit of R. Okay. And then we also said that there doesn't exist a minimal deterministic book keyword automaton. Like you have a canonical DFA, for example. So similarly for DBW, we don't have, we don't have something which is canonical. As an example, we looked at this language which has infinitely many A's and infinitely many B's, and then we, first of all, you can try to figure out that there doesn't exist an automaton, a DBW, with two states which will accept this language. And if you consider automata with three states, then indeed there exists some, but there exist many of them. That's the thing. And this is a result which I think I would recommend that you can try to read yourself. So what do you know about, for example, when we say minimization of DFA? So what is the complexity of that? Kind of. It's a polynomial time thing, right? In P time you can do it. But deterministic book keyword automata, if you try to minimize, that minimization problem is NP complete. I'll post the reference of this paper. I mean, it's not very difficult to read. You can read yourself, right? If you know what is non-deterministic polynomial time. It's essentially you will have to show a membership and then you will have to show a hardness. And you can read it yourself and try to see how much you understand. It should be quite easy, I believe. Okay, this I think it's a result from 2001, early 2000. Yeah. Okay, good. So then we also say like, so deterministic Buki automata that cannot accept this, recognize the language of finitely many years, but can we change the acceptance condition and so that a deterministic automaton can accept such languages with this changed acceptance condition. And so as an example, we talked about this CoBuchi condition. So what is a CoBuchi condition? Now you have a set alpha, but this set alpha should be visited only finitely often, right? This set alpha should only be visited finitely often. So now if you consider such an automaton, right, where this is some alpha state, but this state should be visited only finitely often, right? So then I think it's clear enough that if you have a run, so first of all, you see that it's a deterministic automaton. If you have a run which visits this state only finitely often, then all you can accept is finitely many years. Okay? So this acceptance condition we will be calling CoBuchi condition. And automata with such CoBuchi acceptance condition, we'll call them CoBuchi automata. Right. So This is so now we are going to look at some different acceptance conditions. When I say different from Bushi acceptance. Okay. So the state space of the automaton, I'm referring to that as Q. So that's the general notation we have been using. So again, what is CoBuchi? It's like alpha is a subset of Q, and then we say that a run is accepting if it visits alpha only finitely often. Right? Infer is the set of states which are visited infinitely often by R. Right? So if this intersection is empty, that means that the run visits alpha only finitely often. Okay. Good. Now, there is another acceptance condition which is called the generalized Bushi. So, what is generalized Bushi? Now, here, this set alpha, it has some alpha i's, like some alpha 1 to alpha k. So, there are k sets. So, it's a set of k sets where each alpha is again a subset of Q. Okay. Now, you say a run is accepting if that run visits each of these alphas infinitely often. Okay? So in far, intersection of alpha is non-empty for every I. That is what we will call the generalized Bushi automaton. Okay. The next one we are going to look at, it's called the Rabin acceptance. It's a Rabin acceptance. Okay. So Rabin acceptance will have some pairs of sets of states. Okay. Say for example, there is an alpha I and a beta I, right? And there are k such pairs. K is called the index of the automaton. K is called the index of the automaton. So the Rabin index here is k. And now I say that a run is accepting if there exists some I such that it visits alpha I infinitely often, but it visits beta I only finitely often. So again, so you have k such pairs, and the run is accepting if there exists some pair, such that it visits alpha I infinitely often and beta I only finitely often. Okay.
Alpha and beta are states, right?
Alpha and beta are sets of states.
Okay.
Okay. Yeah. So I think it's mentioned here. Alpha and beta are sets of states. Okay. So when I say it visits, it means that the intersection with alpha I, the inf of R with the intersection of alpha I should be non-empty. Okay. Visit alpha I infinitely often and beta I only finitely often. There should exist such a. And the Streett condition is just the opposite of it. Right? Now I'm saying instead of there exists, for all I, alpha I should be visited finitely often or beta I should be visited infinitely often. Right? Earlier in Rabin, what was it? I was saying alpha I should be, there exists some I such that alpha I is visited infinitely often and beta I is visited finitely often. Now, if you take the negation of that, so there exists become for all, the conjunction becomes a disjunction. Okay? And then you are saying that the alpha I should be visited finitely often and the beta I should be visited infinitely often. Right? Now, if you look at this conjunction, right? So, in general, you also know that something like a negation of P or Q. Okay? Or let me put it like this. P or Q is the same as negation of P implies Q. Right? So this is the same. Now what I'm saying that if there is such a disjunction, so that means for every I you are saying that this is visited finitely, alpha I is visited finitely often, or beta I is visited infinitely often. You can write it in the implication form that for all I, if alpha is visited infinitely often, then beta is also visited infinitely often. Right? It's just easier to remember that way. I'm saying if alpha is visited infinitely often, then beta I should also be visited infinitely often. And this should hold for every I. Okay? So this is a Streett condition. So Rabin and Streett are just opposite to one another. Good. Now we will talk about a parity condition. Okay, so the next thing is we are going to talk about a parity condition. So what is the parity condition? So essentially here you have alpha 1 to alpha k. Again, the index of the parity automaton here is k. And alpha 1 to alpha k, they make partitions of q. I'm saying alternatively, you can also think of like this, that alpha 1 is a subset of alpha 2 and like this, where alpha k is equals q. So why I'm saying alternatively, like, so partition is of course not like one is a subset of another, but we'll see that they are kind of the same. I mean, they're equivalent in some sense. Like you can easily see that they are how they are related. Okay, so okay, I'll come to that. Now you say that a run is accepting if the minimal index I, which is visited infinitely often. Okay, the minimal index I. So you have, suppose there is a run which is accepting, let's say, alpha 1, alpha 2, alpha 4. Okay, infinitely often. Some state from alpha 1 infinitely often, some state from alpha 2 infinitely often, some state from alpha 4 infinitely often. Now, what is the minimum index which is being visited infinitely often? 1, right? So 1 is not even. So I will say the run is not X. Okay. On the other hand, suppose there is a run which visits alpha 2, alpha 4, alpha 5 infinitely often, then 2 is the minimum index which is even. So I'll say the run is X. Clear? Now, so all these things you can see that I'm saying that the minimal index is even or the minimal index is odd. They don't really matter too much, in the sense that suppose if it's the case that I am marking something starting with 0 and I'm defining that the mean has to be even, like this particular thing, right? And now I say that if instead of that, I say the mean has to be odd, instead of 0, I could have marked it with 1, right? I could have just added 1 to all these parity, these priorities. I mean, when I say what is a priority, essentially the index, I'm calling it a priority. So a set q, sorry, yeah, a state q has a priority I if that q belongs to alpha I. Okay, the minimum index set is, let's say, I. Then I'll say q has a priority I. So if I just change the priority here, let's say I add by 1, then the same thing becomes minimum should be odd. Okay. And again, the mean and the max also, they don't differ. Like instead of like whatever you were calling 0, you could have called that k and then just reversed the thing.
That would be harder, right? Because the inclusion is this way.
Yeah, I mean, now you will say the inclusion will be in another way.
Okay.
So all I'm saying that it's just a matter of like making some small changes. Okay.
Yeah.
I mean, so I was talking about the inclusion, but I can also think of this partition in the sense like one particular, uh, let's say one particular state has a value, I'm giving it a priority of, let's say, 0. Another state, I'm giving it a priority of 1. Another state, I'm giving it a priority of 2. So I can also partition them. Okay. Now, how are they related with this other definition? How are they related? Like I can just suppose if I'm giving it, suppose a priority of 0 when I'm saying it's partitioning, right? So it will only belong to alpha 0, but it won't belong to alpha 1. Okay, if I'm giving it a priority of 1 in this definition, making partitions, then I will say that uh, I mean, if it has 1, uh, sorry, it should be the other way around. So if it is 1, then it should belong to alpha 1 and not in alpha 0, right? It's a superset, like alpha 0 is a subset of alpha 1 is a subset of alpha 2, and so on, right? So if I'm giving it a priority of 1, then it should belong to alpha 1 and not to alpha 0. That's it. Okay. So now on, I mean, just to, like, I think it's a way of interpreting things. We will go ahead maybe with this definition of partitioning. right? I mean, it's just, I find it a bit simpler, but it's not necessary that you might find this, the thinking this way maybe a bit simpler, whatever. I mean, but they are equivalent in some sense, right? That's all I'm saying. Okay, good. And the Muller condition is essentially like, it's again like a Muller index. You can talk about an index K, and alpha I is a subset of Q again. So it's a set of states. And now you say that a run is accepting if there exists an index such that the set of infinitely visited states in that run, it is exactly equal to one of the alphas. There exists an I such that inf of R equals alpha I. So that is the Muller condition. Clear? So we looked at the CoBuchi, generalized Bushi, Rabin, Streett, Parity, Muller. So many conditions. Okay. So now what we'll try to see is that if they are somehow related, okay, if they are somehow related. So again, I mean, I talked about the index. What is an index? For generalized Bushi, Parity, and Muller. So these are all these K's that are appearing here, right? For Parity and Muller. So these are like, you have these many sets, and how many sets? So that gives the index. And for Rabin and Streett, it's the number of pairs. That's called the index of the automaton. Okay. And now I think during the last class we were saying this, right? Like the CoBuchi acceptance condition, in some sense, it's a dual of the Bushi acceptance, right? So if you consider a deterministic Bushi automaton with some alpha, with some set of good states alpha, and if you consider a deterministic CoBuchi automaton, the same deterministic CoBuchi automaton, where the alpha is interpreted as CoBuchi states, which means that a run is accepting if it visits that alpha only finitely often. So now you can see that if a run which is being accepted by the Bushi automaton, it will be rejected by the CoBuchi automaton and vice versa, right? It's the same automaton A I'm talking about, same state space, same transitions, exactly the same automaton. I'm just saying that look at it differently. Once you look at alpha as the CoBuchi states, once you look at Bushi states, right? If a run is accepting for the Bushi automaton, it will be rejecting the CoBuchi automaton and vice versa. Clear? Now, similarly, yeah, I mean, one can say that these Rabin and Streett are also dual conditions. And this is particularly when I'm saying that the language is the complement. It's a complement if you consider the automaton as a deterministic automaton, right? I think it's not difficult to see, we were talking about this, that if you have a non-deterministic automaton, then you may not have the complement language when you are just changing the Bushi to the Bushi states to CoBuchi states, right? In case of a non-deterministic automaton, that may not hold true, because you can have multiple runs. One run is accepting, the other run is not accepting, and so on, right? And when you dualize, then the non-accepting becomes accepting, the accepting becomes non-accepting, and so on. Okay. So far, so good. Now, we'll try to see how these conditions are related. Okay. So, there can be different kinds of transition. So we'll start with a very simple kind of transition where it's just that I will have the acceptance condition, like I have some alpha already defined. Now, how I can use that alpha, okay, to define the acceptance condition for the other kind of argument. So this is one kind of argument. The other kind of translations we will see. So we are going to see different kinds of translations among these various kinds of automata, among these various kinds of acceptance conditions. So this is the simplest kind of thing we'll talk about to start with. So you were just given the alpha, let's say from Bushi, and then if you want to say, oh, how will the Rabin look like? So you define the acceptance condition for Rabin also in terms of alpha. Okay. And yeah, and then the other condition can be like, okay, you have the automaton, like other kind of translation can be, you have the automaton and you say that, well, now when I'm defining a different variant of accepting condition, then I will somehow that may depend on the structure of the automaton. Though I'm not really changing the structure when I'm defining a new kind of accepting condition, but the accepting condition, say alpha, it will depend on the structure of the given automaton, right? And the third kind of translation we will see, which will require changing the state space. Okay, so you are suppose translating from one particular, say, from a Rabin automaton to a Bushi automaton. So given a Rabin automaton, if I'm trying to construct a Bushi automaton, then I might need to change the state space. And so that is the kind of things, kind of thing we'll see, other kind of translations. Okay. So now let's start with the simplest one. That I say. So suppose you are given an automaton, a Bushi automaton, a non-deterministic Bushi automaton, with, let's say, the set of these accepting states alpha, right? So you want to visit alpha infinitely often. So how will a Rabin automaton look like? So what is the Rabin automaton again? So you can have some k pairs. There should exist such a pair such that alpha is visited
infinitely often and beta is visited finitely often.
Right? Alpha is visited infinitely often and beta is visited finitely often. Right. So how do you get that? Anybody among the online participants?
We can consider only one such tuple.
Pair, okay, very good. How should it look like?
And Q should be alpha should be the one that's visited infinitely often, and Q minus alpha visited finitely often.
No, that's not true, right? Because when I'm saying that in the Bushi automaton, let's say, in the Bushi automaton, if you are visiting alpha infinitely often, it's not true that you are visiting only alpha infinitely often. There can be some other states can also be there which are visited infinitely often. So for example, Bushi says inf of R, the run is accepting if inf of R intersection alpha is not empty. That is the only thing. But there can be something outside alpha such that Q minus alpha. It is possible that inf of R intersection Q minus alpha is also not empty. This is also possible. Do you see what I'm saying?
I understand, yes.
Yeah. So that's the Bushi acceptance.
The other should beta should use the empty set.
The empty set. Right. So that is the thing. Clear? So I just say that alpha should be visited infinitely often. And I do not have any other restrictions. When I'm doing the conjunction, it's like another restriction I'm saying. I'm imposing another restriction. So I don't have any other restrictions. I'm just saying alpha should be visited infinitely. That's all. It's as simple as that. What about the Streett condition? So Streett says, what was Streett again? Like you have so many pairs. For every pair, if this is visited infinitely often, if the alpha is visited infinitely often, then beta should also be visited infinitely often.
So it's alpha alpha. Oh no, but it's so for the Streett condition, we will need a alpha which is visited infinitely often, right?
Yeah.
Or if there is no alpha which is visited infinitely often,
Can it just be Q command?
It can be Q comma alpha.
Okay, yeah.
Right? So just let's say we call Q comma alpha. So what does it mean? It means that if some state is visited infinitely often, then alpha has to be visited infinitely often. Right? So if you have an accepting run, if you have a run, the run is anyway going to visit some set of states. Right? If it visits some set of states, then it has to visit alpha infinitely. Right? So putting Q is also, it's not really a restriction. Right? It's like true in some sense. Here you have the set of all states, it's like true because any run will visit some set of. What about parity? So parity, let's say if I try to talk in terms of that partition, which find it, I mean, yeah, let's go ahead with that kind of
So it will be like empty, then alpha, and then Q minus alpha. Keep going.
Okay, so you were talking about that kind of. Okay. So let's say empty
alpha Q.
empty alpha
Yeah.
q. Sorry.
Q.
So this is you give it 1, 2, 3,
Yeah.
right? So yeah, indeed. Yeah, if it visits something only outside this, I mean only outside alpha, it will not get the event priority. So if it has to visit something. Good. So what about CoBuchi to Rabin? So you should visit only finitely often the states. You should visit only finitely often. And Rabin says
Rabin is like one is visited.
infinitely often, and the other one is visited finitely often.
So it's like Q and alpha.
So
Oh yeah. Q
Q
minus
is
alpha.
so now you say Q and alpha, right? So if Q is visited infinitely often
Yes.
and alpha is visited finitely often. Okay, good. What about Streett? So Streett says, so there for every pair you can have multiple pairs. If alpha, like alpha comma beta, some alpha I beta I, if alpha is visited infinitely often, then beta I has to be visited.
Alpha comma phi.
Alpha comma phi, empty set.
Because if it is visiting alpha infinitely many times, then it has to visit phi infinitely, which is wrong.
Okay, that cannot happen. Right? Is it okay?
Yeah.
What about parity?
Alpha comma Q.
Alpha comma Q. So this is like so this is 1, this is 2. The index here is 1, and the remaining, like, yeah, so the index is 2 here. So essentially, then you were saying that if this is visited infinitely many times, then the mean index will be 1, and hence this is not accepted. Right? Okay. Okay, good. So what about generalized Bushy to Streett? What was generalized Bushy again? Like for all of them, alpha 1 to alpha k, for all of them, they have to be visited infinitely often.
Oh, all of them.
All of them.
I thought one of them.
No.
And Streett was for all of
So
them.
if you say one of them
Oh yeah,
has to be,
that's bushy.
that is like union of that, and
Yeah.
it's like a Bushy.
Can it be Q comma alpha 1, Q comma alpha 2?
Okay. So if you say Q comma alpha 1, then so if Q is visited infinitely often,
Alpha.
then alpha 1 has to be visited infinitely often.
And Q comma alpha 2. Q comma alpha.
So if you say Q is visited infinitely often, then alpha 2 has to be visited infinitely often. Q is visited infinitely often. So, right? Visited infinitely often, then alpha k plus c. Oh, good. Right? So these are just very simple kind of like looking at the same automaton and just looking at the alphas, and you just sort of get the acceptance conditions. Right. What about parity to Rabin? So you have these sets, okay, and then you are saying you need Rabin, right? So you are saying that these sets should be visited, like the mean event should be visited infinitely often, and then the Rabin says that there should exist something which should be visited infinitely often, and something should only be visited finitely often. So if it is accepted, like if a parity automaton accepts something, that means the mean priority that you have seen, that should be even. The mean index should be even. So something smaller than that should not be, that should be visited only finitely often. Something smaller which is particularly odd.
So I
Alpha
thought
to
like
alpha
alpha to
one.
alpha one.
Alpha for alpha.
Okay. So you have alpha 2.
Alpha 1. Then alpha 4. Just alpha 3. No, alpha.
contains.
Oh, it's
Alpha 3 contains all of it,
Okay.
right? I mean, this is the thing that you are.
Yeah.
Yeah, I mean, when I look at it, I'm more sort of
Fine.
used to doing the partition. Then it will be a bit more like what you were saying, that you have to take the union and so on. Yeah. Okay. So fine. So and so on,
Yeah.
right? And then alpha k. If k is even, alpha k, alpha k. Okay. Uh,
So will street be if suppose for a odd n, alpha n is alpha n comma alpha
so
n minus
okay, just before we go there, so suppose there is something which is visiting, let's say, infinitely often alpha 4, alpha 3, as well as alpha 2 maybe. Okay, something is visiting infinitely often alpha 4, alpha 3, and alpha 2.
Then we want alpha 1 to be visited finitely many times.
Then I want visited, right? So this will not hold true in that case, but this will hold true if I have alpha 1 finite, because there it's like the Rabin condition is there should exist one such pair for which this should hold true, right? That alpha, like the alpha I is visited infinitely often and the beta I should be finitely often. So we are right, and I'm just saying that just to point it out clearly. Okay, what about the Streett condition?
Will it be alpha
Uh,
1 alpha, oh sorry, alpha 3, alpha 2, alpha 5, alpha 4, like that?
So if alpha 3 is visited infinitely often, then alpha 2 needs to be visited infinitely. Very good. And
But alpha 1, we are not using it for this time.
so
we can make something like alpha 1 and
Alpha
anti
So
alpha
if
1 and
alpha 1
phi.
is visited, then pi should be visited, so that.
no, how what does it mean is phi cannot be visited.
So alpha 1
Right?
cannot accept pi.
Okay. So if alpha 3 should be okay, yeah. So if alpha 3 is visited infinitely often, then alpha 2 is visited infinitely often. Right? But if alpha 1 is visited infinitely often,
Pi should.
Right.
then
We give a false
yeah.
statement.
Okay. Right, and so on. Let's say this is if k is I don't know here, if it's so if k is even, then what can we do? Like we can say that
Okay.
we can add an extra priority to it or something like one possible thing is like we can always shift it by 1. We can always do that. We can just shift it by 1 and we'll be fine. Right? And we can define it that way. Yeah, so yeah, so if k is odd, then this is the thing. If k is even, then we can shift it by 1 and then we can put it like this. Okay, this is fine. Okay, so what about the next one? So Bushi to Muller.
But what is Muller?
So Muller was like you have set of sets of states, right? So you have like some f1, f2, fk, or yeah, maybe we were using alpha 1, alpha 2, alpha k, like this. And then we were saying that there should exist some I such that inf of r equal to alpha r. So it's exactly, it should match with exactly one of these sets.
One way to do it is just consider all possible subsets of alpha
subsets or
subsets of
okay,
the alpha.
subsets. Okay, and then
And then that will be our F1, F2, Fk. So all possible non-empty subsets of alpha. And then
is that sufficient? Like, so suppose my alpha is, let's say, some states Q1, Q2, Q3. Now, what you are saying is that just Q1, Q2, Q3, and Q1, Q2, Q2, Q3, Q3, Q1, and
Q1, Q2, Q3.
Q1, Q2, Q3.
Yeah.
Suppose if I had some other states like Q4, Q5, which are not part of alpha, then
Right.
is it clear among the online participants? Are you all following me?
Yeah,
far?
yeah. We should create, we should consider all combinations of the non-accepting states as well.
Yeah, exactly. Right. Yeah, you are right, Rishab. So you should consider all the supersets also, such that like every pair of sets Q, such that Q intersection that alpha is non-empty.
Okay.
Okay.
Yeah.
So it's a set of all such maybe I'll say Q prime, because Q I'm using for the set of states, such that Q prime intersection alpha is not empty. Okay. So this is the thing. What about CoBuchi to Muller?
Then
Same thing, but
they don't have any of the alpha states.
all sets such that its intersection with the alpha sets is empty.
All sets such that intersection with the alpha.
Alpha is empty.
Okay, good. What about parity to Muller? So it's like you were saying that suppose if that something from alpha 2 gets visited, things below should not be, I mean,
Yeah.
states with the index. I mean, you can just essentially have to
Yeah.
write all the combinations.
Yeah.
Then you can do that. Good. So I'm not writing that, but I think it's clear enough. We just have to. What about Rabin to Muller? So suppose if you consider some, let's say, you consider some alpha I beta I. Okay, so this should be visited infinitely often, and this should be visited finitely often. You can again think of all the
same thing.
all the possible sets of states which will satisfy the Muller condition, right?
The intersection with alpha should be non-empty, intersection with beta should be.
Beta should be empty, right? Okay, fine. And then for so how many like, so when I say F1 to Fk, we are going to get exactly the index is going to be the same, right? So number of pairs here is k. In the Muller automaton also we are going to have the same index, correct? Okay, okay, good. Is it true,
It have
or is it going to have more?
Oh yeah, it would have more.
because you're taking subsets, all kinds of subsets.
Yeah,
All kinds of subsets, right? So you're going to have more,
much more.
number of the index of the Muller automaton is going to be much higher.
Yeah.
Right? Possibly, maybe, I don't know, exponential many possibilities.
That's the case in the other things also, right? Like
They got
Bushi,
vectors.
CoBuchi.
Yeah. Right? Okay. Okay. So similarly, you can also do it with the Streett. So essentially look at all the different possibilities and then find out which set of states you may have. Okay, is it clear? Any question from the online participants? Any question? Okay, if not, so let's move to the second kind of translation. So the second kind of translation is like I'm saying that there are two classes. So when I say two classes, two kinds of acceptance conditions. And I'm saying that gamma is K type if for an automaton, for a gamma automaton A, if for a gamma automaton A, gamma automaton A, there exists K automaton A prime such that LA equal to LA prime, then there also exists K automaton A double prime with LA equal to A double prime, and A double prime differs from A only in terms of the acceptance condition. Is it clear? The definition. So what I'm saying is that like for this gamma is of K type, it's not necessary that every automaton with the gamma acceptance can be translated to an automaton of the K with the K acceptance condition. But if it is the case that corresponding to a gamma automaton, there also exists an automaton which has the acceptance condition of the K kind of acceptance condition, then there also exists an automaton of the K kind, K type, which looks exactly like the gamma automaton, but the acceptance condition will only differ. Okay, the state space, the transitions, everything will look the same, but the acceptance condition will differ. Okay, so essentially, like the previous classes, the previous set of translations that we saw, they belong to the same kind also. They also belong to this type also, right? This type of translation. Is it clear? So what I'm saying is that it is of K type if for a gamma automaton A there exists a K automaton A prime such that they have the same language. Then there also exists another automaton A prime such that their languages are the same and A prime differs from A only in terms of the acceptance condition. So the underlying things are the same.
But it can happen that for a gamma type automaton, there is no K type automaton.
That can also happen. That can happen. But here there is a condition. It's a conditional thing.
If
If there is one, then there also exists one which looks similar. The underlying graph looks similar. The only thing that changes is the acceptance condition. Okay. So now, so I'm saying that this typeness trivially follows for all the previous translations also, what we saw, just by changing the acceptance condition. We were just interpreting earlier the acceptance conditions differently for different kinds of automaton, right? So of course, like if we had, for example, parity to Rabin, correct? Then it also says that parity is of Rabin type. It says parity is of Rabin type. Okay, but now here it can also be the case that there are certain kinds of acceptance conditions which are more expressive in some sense, in the sense like you can easily translate one to the other, but the other direction may not hold true. Even for that also, it can be possible that, like, so yeah, I mean, even if gamma is more expressive, then also it can happen that gamma automaton can be of k type. Okay, so we will see that deterministic Rabin automata, Rabin word automata, for example, it captures all of omega regular languages. So DRWs are as expressive as NBWs. Okay, and at the same time, we are saying DRWs are of DBW type. So we are not going to look at this result in full, I mean, not the full proof, but I'll just tell you about some proof skates. Essentially because, yeah, I mean, you can always go back to the chapter and try to figure it out, but there are other important things also we would like to cover. So essentially, like, you see that DRWs are more expressive than DBW, because as I said, like, DRWs are as expressive as NBW, but DRWs are DBW type. So what does it mean? It means that corresponding to a DRW, if there exists an equivalent DBW, right, automaton corresponding to a DRW automaton, if there exists an equivalent language, if there exists a language equivalent automaton, an equivalent automaton, then there also exists one DBW automaton which will look exactly the same, just the acceptance condition will be different. How do you determine the acceptance condition here? The acceptance condition here depends on the structure of the original DRW automaton. Is it okay? Like, it depends on the structure. Like, there are some structural properties which might be there, which will determine the acceptance condition of the DBW. Okay, so that's the thing. Now, the idea is the following. So how do you construct it? So suppose you have the DRW, which is like this, Q sigma, Q0, delta, and the alpha. So alpha, you recall here, it's if the index is k, then you have k such pairs, alpha by beta, right? So it's like this. And now we say a state Q is good in this DRWA. Why we are defining this good state? Because this is what is going to define the acceptance condition for the DBW that we will have, right? It is good in A if all cycles in which Q appears, that satisfies the alpha condition of the DRW. A state Q is good. So a state Q appears in different cycles, right? It can appear in different cycles in the underlying graph of the automaton. So I'm saying that this state Q is good if all the cycles satisfies the alpha. So when I say all the cycles satisfies the alpha, that means that this C intersection alpha I should be non-empty and C intersection beta I should be empty. There exists such an I such that C intersection alpha I should be non-empty and C intersection beta I should be empty. Okay? And the state Q is good if for all these cycles, this thing holds. For every cycle, there exists an I such that C intersection alpha is not empty and C intersection beta is equal to empty. So one can show that if you now have the DBW where the alpha is defined as the set of such good states Q, okay, then you can indeed show that such a DBW is equivalent to the input DBW. Okay, so you got the idea of like what do we mean by saying that DRWs are DBW type, right? I'm not going through the proof in detail. I mean, you can see that in the chapter if you are interested. But I mean, I think it gives us an idea of like when we talk about the typeness, what it essentially means. It says that, okay, like the underlying automaton remains the same, but the acceptance somehow depends on the structure of the input automaton. Okay. And now I'll just talk about another result which says DSW. So what is DSW? Deterministic Streett word automaton, right? And what was Streett automaton again? Like you have such k pairs, alpha I, beta i's. For all I, if alpha I is visited infinitely often, then beta I also has to be visited infinitely often. So we are saying that this is not DBW type. So just by looking at this automaton, when I'm saying that if Q0, Q1, so essentially if entire capital Q, the state space is visited infinitely often, then Q1 also has to be visited infinitely often. And if Q0, Q1 again, if this is visited infinitely often, then small Q0 also has to be visited infinitely often. Now, if you interpret this automaton as a Streett automaton, then what is the language that it accepts?
Infinitely many A's and infinitely many B's.
Very good. Infinitely many A's and infinitely many B's. So this is the language that it accepts. You recall this language? Do you recall this language? We saw this somewhere, sometime back. In what context?
Trying to complement the automata which has finitely many A's. But no, something we were trying to do.
No, not exactly.
Not that.
That gave infinite.
So where did we, does anybody remember among the online participants also? Where did we see this language?
In the subset
Infinitely
construction,
A's and infinitely many B's. If I go up a bit above, I think I'll be able to, will be able to see. Huh? So let's see.
The
Infinite.
minimum 3 states.
Exactly.
Right.
Right? So, so this was the language, right? Infinitely many A's and infinitely many B's, and we say unique minimal DBW may not exist, right? So now you see that we have a deterministic Streett automaton. We have a deterministic Streett automaton which has two states, and it accepts that language. But we also say that if you consider DBW, there doesn't exist a two-state automaton accepting this language. Hence, DSWs are not DBW type. Okay? Clear enough? Good. Okay. Now, what are the results that we saw? Two things we saw. One is DRWs are DBW type and DSWs are not DBW type. Okay. So now if you just look at the DRW automaton and you just sort of dualize the acceptance condition. So the DRW becomes DSW and you have the DBW, correct? So if you have the DBW, if you dualize that, right? A run that is accepting here will not be accepting there. And similarly, a run that is accepting in the DBW will not be accepting in the DCW, right? So what do we exactly get? We get that DSWs are, so from this we get DSWs are DCW type. Just as a corollary, as a simple corollary, right? Because a run that is accepting here, now you interpret with some different alpha, you get like a DBW, or you will get that run to be it's accepting there with a different alpha. Now you are saying that if you now dualize, so the run will not be accepting there, and similarly in the DCW also it will not be accepting, and hence we get that DSWs and vice versa. If it is accepting in the DSW, it will also be accepting in the DCW, right? And so why do I say the run? Because on the word, it's a deterministic automaton. You have only one run. Okay, you have only one run, right? So the DSWs are DCW type. It's clear. We are just dualizing the acceptance condition. And similarly, we also get that DRWs are not de Sitter orbital. Right? So this is what we write. Okay. So we'll just end this second type of translation here. I mean, I think we'll study relatively. You can find more details in the chapter, and then and there are some other kinds of results also. But now we will move on to translations which will require some new state space, additional states. Okay, so let's start with a very simple kind of a translation. So consider a generalized, non-deterministic generalized Buki automaton with n states and index k. Now, how can you translate it into an NBW? Is it clear? Like you are given a non-deterministic generalized Buki automaton, and I want to construct an equivalent Buki automaton. I might have to, the state space now, I mean, I'm allowed to change the state space. I can add additional states. How can I do that? Okay, somebody had a question, sorry. The subset construction that we did.
No, no,
Sorry.
it was not a question. So I wanted to answer the question that you asked.
Okay, but you can just yeah, I mean, I'm not looking at the chat all the time. You can just say that. So this is in the context of what?
Uh,
Complete.
Previously, you asked like, why did you see the automata before?
Sorry, I didn't get you. Which translation you were talking about?
Hello?
Hello, yes.
Yeah, sorry, my mic was echoing. So I was saying, so previously you asked like, where did you see that automata before? So
Oh, I see. Okay, okay. Okay, no, it was actually for that minimization part.
yes, yeah, yes, right.
Okay, so how do we do this translation from a generalized Buki automaton to Buki
You can
automaton?
have like k copies.
You have like k copies.
First one has the accepting one
Yeah.
has only the alpha 1 states.
Right.
And second one the alpha 2 states. So wait for it. And then like same like we
Right.
did for the
Yeah. Right. So you have n states and index k. So you make k copies. So in total you will have n k states. Right. So when you see an alpha 1 here, state in alpha 1, you go to the second copy, you see their alpha state in alpha 2, you go to the third copy. What will be the acceptance condition now?
Just pick any of
Pick
the
any of
copies
them.
and
Right.
the
Let's say the first one, any of them, doesn't matter. Yeah. Good. So is it clear to everybody? Right. So I just wrote that only here. Right. So is the construction clear to everybody? So essentially you are making, so if you have, let's say, the original automaton, it's like this, and you have, this is the generalized Buki automaton, and you have this, let's say the acceptance conditions, alpha is alpha 1, alpha 2, alpha 3, alpha k. So now what was suggested is the following, that you make k copies in the Bushi automaton, right? So alpha 1, I mean, sorry, copy 1. So this is the first copy, second copy, like the kth copy. And whenever you visit some state in alpha 1, you just jump to the second copy. You visit some state in alpha 2, you jump to the third copy, and so on, right? And when you visit some state in the kth, visit some state alpha in alpha k in the kth copy, you come back to the first copy, right? So how do the translations look like? So essentially, A was my input generalized Bushi automaton. So it has these k sets, alpha 1 to alpha k. A prime is of the form q prime sigma q0 prime delta mu alpha prime, and q prime is q cross 1 to k. So you have k copies. And I start, so my initial set of states is q0 cross the set of initial states in the first copy. And now if I look at the transition, so delta prime qi comma a, it remains in the same copy if q does not belong to alpha, and it goes to the next copy, right? When I say I mod k, it's like you go to the next, and from the last one you come back to the first copy if q belongs to alpha, and the set of accepting states is alpha cross I. Right? It's quite straightforward. What about this one, like non-deterministic Rabin automaton to an NBW? Suppose if I have a Rabin automaton and I want to construct a Bushi automaton. So what is the Rabin again? Like, so there exists some I such that alpha I is visited infinitely often and beta I is visited finitely often. And there is a disjunction here. Okay. So can you use the disjunction in some way, some nice way? I can give you a hint. So which is like non-deterministic Bushi automata, they are closed under disjunction. Non-deterministic Bushi automata are closed under disjunction. So what can you do?
So we want okay, let me think.
Yeah. So let's say you would like to translate a non-deterministic Rabin word automaton with one index, with a single index, to a non-deterministic Bushi word automaton. If you can do that, then if you have k indices, you can do just, you do that for each of them and take the disjunction, right? So now the question is that if you are given a non-deterministic Rabin word automaton with a single index, how can you translate it to a non-deterministic Bushi word automaton? So something is visited infinitely often and something is visited finitely often.
So finite, we can again do the two copy thing.
Right.
And then we know from all the betas, like we will eventually go to the second copy, which does not have the beta states. And that will ensure that, and the accepting states will be the alpha states in the second copy. So then the run ensures that beta is visited finitely often, alpha is visited infinitely often.
Very good. So everyone among the online participants, could you follow? Could you follow what it said?
Yes, I got it.
Right? So yeah. So what you have is like you make two copies. In the first copy, you have all the states. In the second copy, you don't have the beta states because beta, they are going to be visited only finitely often. So at some point of time, non-deterministically, you can jump to that second copy. And in the second copy, you have to visit the alpha states infinitely often, right? Because the alpha states in the Rabin automaton, they need to be visited infinitely, right? So let's look at the construction just a bit formally. So as I said, like, so I'm going to do this like LA is a union of LAI, I going from 1 to k, and AI corresponds to like the pair alpha I beta I, right? A run which will be visiting alpha I infinitely often and beta I finitely often. So since NBWs are closed under union, it suffices to consider NRWs of index 1. Okay. So you have exactly this, everything in the first copy. In the second copy, you don't have the beta states. And then the initial states are in the first copy. And now when you are doing the translation delta prime q comma 0 in the first copy, you do an A. So you stay in the first copy as well as you have like these are non-deterministic transitions. As well as you go to the second copy, but in the second copy you don't have the beta state. So you remove them in the second copy. And when you are in the second copy, then again in the second copy also you don't have the beta state. So you remove them and you stay in the second copy. In the second copy, you always stay there. You never come back to the first copy, right? And then, as you said again, like the alpha states are those in the second copy, right? Okay. So 0 stands for the first copy, 1 stands for the second copy. Clear? Good. Now, time for some more thoughts. What about NSW to NW? So now you are, instead of a Rabin automaton, I'm giving you a Streett automaton.
Sir, I have a doubt in the previous thing.
Yes.
Like, alpha I, beta I, it's not like beta I's are disjoint, right?
Yeah, you are right.
So, it can visit beta I states finitely many often in that set
Ah.
of ones, but now we are making like k copies kind of a thing. This is for one,
Yeah.
and then we are making k copies for each. Oh, wait.
But this is a disjunction.
Okay.
This is a disjunction.
Okay.
But you are right that alpha I, beta I, the intersection it doesn't have to be empty necessarily. That's true.
No, I got confused. I now.
Okay. Oh, good. So what about non-deterministic, Streett to non-deterministic
This
Bushi?
is the. I was thinking this since while I was.
Okay. So what about Streett to Bushi? So earlier, what did we do? We did like, so when you have k indices, you took the disjunction of like L is the union of L of A is the union of all of over the L of AIs. And you translate this one index NRW to NBW and then take the union. What is the condition for NSW? What is the condition for NSW?
Like,
You have the intersection for all of them. Like you have the, so if alpha I is visited infinitely often, then beta I also has to be visited infinitely often. You have to consider, okay. So suppose now I also do the decomposition, right? I do the decomposition and I construct NBW index by index, right? So you are given a single pair, alpha I, beta I. I consider the non-deterministic Bushi word automaton. So if alpha I is visited infinitely often, suppose I do that.
but here, how do we combine all the?
So non-deterministic Bushi word automaton are closed under intersection also.
Oh yeah.
I can get everything.
Okay, so for the separate thing, so there are two cases. The in our intersection, the alpha I can be empty or non-empty. So if it's empty, then we will go to a copy in which the alpha states are removed. And yeah, that's all. Anything in that will be accepting state in the second copy.
Could you say that again? Like,
So there are two possibilities that if our intersection alpha I is empty or non-empty. So let's say it was empty. Then in that case we will go to another copy of that, of the original automata. And in that copy all the inf states will be deleted.
So
No, alpha I states are deleted.
Sorry, alpha I states are deleted. And all the remaining states are just accepting states.
So what do you have in the first copy? You have all states.
It's just the automata which we will give.
You have all states, and then you are saying that.
Eventually it goes to this.
Okay.
Or the other condition is the intersection is non-empty. So there will be a third copy like this. And
So you're talking about a RAM, like essentially how
yeah,
the RAM.
yeah.
So you have one copy where what do you have?
Like we'll need 3 copies. The one copy will point to another copy or the below one copy.
Okay, so it's going to here and here.
So we'll go to the first copy if the intersection is empty.
Okay,
And then that copy is delete the alpha I states and make all the other states accepting states.
okay. So okay. So if alpha is, so we are saying if alpha is visited infinitely often, then beta has to be visited. So if alpha is not visited infinitely often, then everything is fine.
Yeah.
Okay.
Or the other condition is it is visited infinitely often. So okay. So now this is just the intersection of languages accepted by the same automata with alpha as the accepting states and the same automata with beta
Beta
as
as
the accepting states.
So here you are saying you are removing here you are saying you are not removing anything. Like in this one, everything
Yeah.
is there.
No, there we
alpha
are
is
doing the
states.
alpha states.
There's no alpha.
Yeah.
Okay.
And now the second case, what we want is we want automata, we want a run which visits alpha infinitely many times and beta infinitely.
Right.
This is the intersection of
Okay.
the two automatas.
So you want that alpha I intersection beta I, so that should define the acceptance
Yeah,
function,
yeah,
right? And then you were saying that you take the intersection
yeah,
and then you,
yeah.
okay? So now I say that it won't work. It's not correct. Okay, so even before you come here, before you take this intersection, you define this and you are saying that I take the intersection. I'm saying that this entire approach of taking the intersection, there is something wrong with. What is incorrect? What is incorrect?
Was it like in that copy it will accept alpha infinitely, but in another copy finite? Like, okay. No,
So, okay, so let's go through what is the, when is a run accepted?
if
When is a run accepted?
it's accepting alpha infinitely many times, then it accepts beta also like intersects with beta also infinitely.
And what about the quantification? What about the quantification? What about the I mean the quantification here I'm talking about this quantification.
For all.
So can you say that again once more fully?
For all I, if in intersection.
So a run R is accepted if for all I.
If our intersection alpha is non-empty, then if our intersection beta is also not empty.
Yes. So I'm talking about that there is a single run which has to satisfy all the conditions I. So there is a single run R which has to go and satisfy all the conditions, right?
Because in another copy that we are making, it could be like alpha is accepted infinitely many times and beta is accepted finitely many times, but that won't consider it the same thing.
So the thing is that if you consider the intersection, right? Like for every pair, now suppose I do that I'm constructing, suppose some Bushy automaton NBW, right? Corresponding to let's say B1, B2 like this, BK, and each of them corresponds to this alpha 1, beta 1 here, right? Then alpha 2, beta 2 here, like this. Okay. It may be possible that a word W here, when it is accepted by this automaton, right? I'm just considering this and translating this to this B1, right? A word W which is being accepted by this one index Streett automaton. There may be another, suppose there is a word W which is this one index DSW, then there may be another, the same word also may be here in this one index DSW. Sorry?
It might not even have the same run.
Yeah.
It might not even have the same run, right? It might not even have the same run. So it may be possible that you have this word and this has a run in this DSW and it satisfies this alpha 1 beta 1 condition. and the word may have a different
Mm.
run in the other DSW. Okay, and if you take the intersection, this word will be in the language,
The run would be in the
but the
language.
run is not there in that, right? So hence this whole idea of intersection does not really work. So I was talking about DSW, sorry, it should be rather NSW, right? I mean, we are talking about NSW to NBW, right? So you have an NSW with one index NSW, you have another one index NSW. It may be possible that there is a word which belongs to this one index NSW, as well as there is and the same word also belongs to this one index NSW, but maybe the runs which are satisfying these acceptance conditions, they are different. Okay. Now, if you take the intersection of the two, this word will belong to that intersection, but the word is not originally accepted by that NSW with K indices. Clear? So this intersection approach doesn't work. Okay. So we are out of time. So next lecture, I think we are going to look at this. This construction is going to be like a lot more interesting compared to the constructions which were more like warm-up things we had. And we will also see, first one thing we'll see is that it gives you an exponential size blow up. An exponential blow up you will see when you are doing the NSW to NPW. So far, all we were doing was like NK, etc., all polynomial blow-ups, right? Quadratic blow-ups and things like that. So this is the first time we are going to see that when we are translating an NSW to an NPW, we are going to have an exponential blow-up. And not only that, we'll see that this exponential blow-up is inevitable. So what do I mean by that? How am I going to show that?
Family.
Some family of NSW such that every NBW which will be equivalent to that, right, for that language, like some ln I will start with, like where n is of course the parameter for every integer, let's say n. So when I have this ln, the corresponding NBW will have at least exponentially many states. So we are going to see both of them during the next class. Yeah. So I wanted to finish both of them today, but I will not do that. And so yeah, I'll do that during the next class, which will be on Friday at 9:30. Right. So before we end, any question from the online participants? Do we have any question? Okay. Rishad, everything is fine so far? Shanthan, I hope yeah, things were okay.
Yeah, mostly I've understood it. I will take a look and
Okay.
I think things will be clear.
Okay. Okay. So if there are no more questions, I'll just stop the recording now.